This section examines diesel fuel injection. All diesel engines draw air only past the intake valve into the cylinder. A high-pressure fuel injection system injects fuel into the cylinder. The amount of fuel injected is varied to suit the load on the engine and to control engine speed. Intake air volume does not change. In a basic diesel fuel system, a fuel tank holds the diesel fuel. A lift pump takes fuel from the tank. It keeps the injection pump full of fuel. A sedimenter removes any water and larger particles in the fuel. A fuel filter removes minute particles. An injection pump delivers fuel under very high pressure to the injectors along injector pipes. It must send the correct amount of fuel, and it must send it at the correct time in the engine cycle. An injector at each cylinder sprays fuel into each combustion chamber. Leak-off pipes take fuel used for cooling and for lubrication from the injection pump and injectors back to the tank. They also help to remove air from the system. A governor controls engine speed, and a control lever on the governor is connected to the accelerator pedal. The basic system is divided into two sections. This is the low-pressure side. The low-pressure side cleans the fuel and delivers it to the high-pressure side, or fuel injection system. Dirt and water will damage a diesel fuel injection system. The highly polished components need a very efficient filtration system to ensure all traces of dirt and water are removed. The highly polished finish is achieved by lapping two components together to form a matched set. Matched components must not be interchanged after lapping is completed. The high-pressure side of the fuel injection system must raise the pressure of the fuel high enough to open an injector. This allows the fuel to be forced into the combustion chamber at the correct time. A light automotive diesel engine typically has a higher compression ratio than a comparable petrol engine. This high compression ratio heats the air in the combustion chamber to a temperature high enough to ignite the fuel when it is injected. High injection pressures are needed to overcome the compression and combustion pressures in the combustion chamber and break up the fuel into small particles. Because of these high pressures, the injector pump and the injector are made from highly polished and accurately sized components. The injector pump can be an inline type, and it is driven by the engine. Or it can be a rotary type, also driven by the engine. The quantity of air taken in on the intake stroke is not controlled by the driver. The driver controls how much fuel is delivered to the engine. A characteristic of all diesel engines is that at a fixed fuel setting, the amount of fuel delivered to the engine will increase as engine speed and pump speed increases. This is called the rising characteristic of the fuel injection system, and unless it is controlled, overspeeding of the engine will result. Also, because combustion pressures are greater in a diesel engine than in a comparable petrol engine, the components are stronger and heavier. The higher mass of these reciprocating and rotating components needs to be controlled, or damaging forces could be generated. To achieve this control, all diesel engines use a governor to control how much fuel is delivered from the injection pump to the injectors and into the engine. There are several types of governors. Some operate mechanically, some are pneumatic, and some are hydraulic. Diesel engines need assistance to make cold starting easier. Most diesel fuel injection systems inject extra fuel when starting to ensure sufficient fuel will vaporize and burn in the combustion chamber. Indirect injection engines may also use heater plugs or glow plugs, which usually screw directly into the combustion chamber. They only heat the air and do not begin the combustion. This section examines diesel fuel. Like petrol, diesel is a compound of hydrogen and carbon extracted from crude oil. There are different grades of diesel fuel for diesel engines. What is commonly sold in a service station is highly refined and is suitable for use in high-speed diesel engines, including those in light automotive use. The cetane rating of a diesel fuel defines how easily the fuel will ignite when it's injected into the cylinder. The lower a fuel's cetane rating, the longer it takes to reach ignition point. Using a fuel with too low a cetane rating will increase the amount of diesel knock in an engine. When diesel fuel is injected into the cylinder, it does not ignite instantly. It takes time for the heat of the compressed air in the cylinder to heat the fuel sufficiently for it to ignite. This period of time from the start of injection to the start of combustion is called the delay period. During this delay period, fuel continues to be injected into the cylinder. When the fuel is heated sufficiently, it erupts into flame. Combustion occurs. The sudden pressure rise sends a shock wave through the combustion chamber that can be heard outside the engine. This is the sound called diesel knock. Diesel knock can also be caused by poor atomization of the fuel, which can take too long to reach combustion temperature. The higher the cetane rating of the fuel, the easier a cold engine will be to start. The engine will produce less smoke and odors, and there will be fewer deposits in the combustion chamber. Diesel engines are also required to operate in low temperatures. During low temperatures, the fuel becomes thicker. If the temperature is too low, paraffins in the fuel begin to solidify and form waxes. These waxes can block filters, causing fuel starvation and low power output. To help prevent this, filters are fitted close to the engine, and sometimes heaters are used. Diesel fuel also acts as a lubricant for the fuel system components, provided it's free of water and abrasive particles. This section examines tanks and lines. The fuel tank stores fuel in a convenient location away from the engine. It is commonly made of steel or aluminium. Baffles ensure the pickup tube is always submerged in fuel. This stops air entering the system. The inside of the tank can be treated to prevent rust. Galvanizing must never be used because diesel fuel reacts with zinc to produce powdery flakes that can block fuel filters. A diesel fuel tank should be kept full to prevent water condensing on tank surfaces and contaminating the fuel. In light commercial diesel engines, two fuel lines are used. One carries fuel from the tank to the filters and then to the fuel injection pump. The other is the return line. It carries back to the tank the fuel that is used for lubricating and cooling the injectors, the injector pump, and for bleeding the filters. They are usually made of seamless steel tubing, coated with tin to prevent rust. Sometimes cadmium is used instead of tin. A fuel line must be large enough to provide enough fuel flow for maximum power. It's supported under the vehicle by nylon insulators and brackets. Reinforced synthetic rubber hoses allow for movement and vibration of components. The reinforcement is needed because the fuel line is subject to variations in pressure. Injected lines are made of cold-drawn, annealed seamless steel tubing. The bore of the pipe is kept to the smallest diameter possible, and all of the pipes are the same length. If pipes of different lengths were used, it would affect injection timing. This section examines fuel filters for diesel engines. The fuel filter removes abrasive particles and water that could damage the accurately sized and polished injection equipment. The most efficient filtering system uses the first filter to remove larger particles and subsequent filters to remove smaller particles. Water traps and sedimenters trap water and larger dirt particles. They can be separate units or combined with an impregnated paper element filter. Separate units pass the incoming fuel over an inverted funnel. At the edge of the funnel, the fuel changes direction very quickly. Water and dirt are heavier than fuel, so they are trapped away from the funnel edge. They fall under gravity and settle at the base of the sedimenter. The lower housing is usually clear for easy inspection, and it can include a drain plug, so sediment can be drained off daily. The most common type of filter material in diesel vehicles is resin-impregnated paper, pleated to offer a large surface area to the fuel. These filters are also considered the most efficient. In some of the filters that use this paper, fuel flows from outside to inside. In others, it flows from the base to the top. In others, from top to bottom. A fuel filter with the resin-impregnated paper element can be combined with a water sedimenter. When this combined unit is used, the method of fuel flow is determined by the manufacturer. One method has fuel pass through the paper element first to trap abrasive particles. Any water in the fuel is usually in the form of small droplets, which are forced through the paper element. Once through the filter, the small droplets combine into larger droplets and form a sediment layer in the base of the filter. The bowl may be transparent and it contains a drain plug. Other types pass fuel into the sedimenter first and force the larger particles out of suspension by a change in direction. The fuel is then forced through a filtering medium ready for use. The base usually has a drain plug for daily draining of the water from the filter. This type is usually contained in a disposable element. A water level switch can activate a light on the dash to warn the operator the sedimenter chamber may need draining. The switch has a float that is lighter than water but heavier than fuel. In the float is a magnet. As the float rises on the water level in the fuel, the magnet closes a reed switch, which turns on a warning light in the instrument cluster. The operator can then remove the drain plug to drain the water. This section examines fuel lift pumps for diesel engines. The lift pump transfers fuel from the tank to the fuel injection system. In modern vehicles, the tank is mounted below the engine, and the fuel has to be lifted up to the level of the engine. 3 types of lift pump are common on light vehicle diesel engines: the diaphragm type pump, the plunger pump, and the vane pump. The diaphragm type pump can be mounted on the engine or on the injection pump. It is fitted with inlet and outlet valves, and an eccentric on a camshaft acts on a 2-piece rocker arm connected to a diaphragm. Rotating the eccentric causes the rocker arm to pivot on its pin and pull the diaphragm down. This compresses the diaphragm return spring and increases the volume in the pumping chamber above the diaphragm. Atmospheric pressure at the fuel tank forces fuel along the fuel line to open the inlet valve. Fuel flows into the pumping chamber. The eccentric keeps rotating and the rocker arm is released. The spring exerts force on the diaphragm to pressurize the fuel in the chamber. This pressure closes the inlet valve and opens the outlet valve, letting fuel be delivered to the injection system. If the system doesn't need all of the fuel delivered, the pressure in the outlet fuel line rises to the same level as in the pumping chamber. That holds down the diaphragm and keeps the diaphragm return spring compressed. When this occurs, the split linkage in the rocker arm allows the lever to maintain contact with the eccentric without acting on the diaphragm pull rod. A second type of lift pump in light vehicle applications is the plunger pump. It's mounted on the inline injection pump and it's driven by a cam inside the inline injection pump housing. Internally, a spring-loaded cam follower converts the rotary motion of the camshaft into reciprocating motion. The reciprocating motion is transferred to a spring-loaded plunger fitted with close tolerance in a cylindrical bore. It has two spring-loaded check valves, an inlet valve and an outlet valve. As the engine drives the injection pump, the lobe of the camshaft pushes the cam follower into the plunger pump. The cam follower acts directly on the plunger, pushing it towards the end of the cylinder bore. Fuel is displaced from one side of the plunger through the outlet check valve to the other side of the plunger. When the cam follower retracts, spring force on the plunger moves the plunger out of the cylindrical bore. Fuel from the fuel tank enters behind the plunger through the inlet check valve. Fuel in front of the plunger is displaced out of the pump to the fuel injection system. If the quantity of fuel required is reduced, so is the movement of the plunger. A vane pump is used in distributor-type injection pumps. It is also known as a transfer pump. It is mounted on the input shaft in distributor-type injection and pumps fuel whenever the distributor pump is driven by the engine. It consists of a rotor mounted off-center in a pump housing. Slots are machined in the rotor to carry vanes. As the rotor rotates, the vanes can move into and out of the slots. The vanes seal on the edges of the rotor slots and the pump housing. As the pump rotor rotates, trapped fuel is carried around by the action of the rotor until the leading vane uncovers the outlet port. Since the rotor is offset as it turns further, the volume between the vanes reduces and fuel is squeezed out of the pump. A pressure relief valve controls the pump's operating pressure. All diesel engines in light vehicle applications have a priming lever on the lift pump or a separate priming pump to allow for removing air from the fuel system. This is called bleeding or priming. Air can enter the system during filter replacement or when a fuel line is disconnected. Without a priming facility, the start motor would have to crank the engine over to bleed and prime the system. Excessive use of the starter motor for this purpose would damage it, and it would soon discharge the battery. This diaphragm lift pump has a lever that acts on the diaphragm rocker arm. Moving the priming lever moves the diaphragm down. Releasing the lever allows the diaphragm return spring to force the diaphragm up. The action of the diaphragm and valves during bleeding is the same for normal operation of the pump. Since distributor-type injection pumps use an internal vane pump, their fuel supply system incorporates a diaphragm-type priming pump, usually located on top of the fuel filter. This filter housing includes a diaphragm-type priming pump. The diaphragm is connected to an actuating button, and it's held in its uppermost position by a diaphragm spring. Reed valves connect the priming pump housing to the filter. Pressing down on the actuating button reduces the volume in the pumping chamber, which forces fuel into the filter element. Releasing the button lets the spring lift the diaphragm, which increases the volume in the pumping chamber. Air pressure in the fuel tank then forces fuel into the pumping chamber. A plunger-type priming pump is often used with plunger lift pumps that are mounted on inline injector pumps. It can also be mounted on top of fuel filter housings for distributor-type injector pump systems. The plunger-type priming pump consists of a plunger and a barrel assembly mounted on the side of the plunger pump or on a filter housing. This plunger priming pump uses the valves of the plunger lift pump to direct fuel flow. Plunger pumps mounted on the top of filter housings contain inlet and outlet check valves. Pulling the primer plunger increases chamber volume, which decreases the pressure in the chamber below that of atmospheric. Fuel in the tank is forced along the fuel lines, through the inlet check valve and into the pumping chamber. Pushing the plunger into the barrel decreases the volume in the chamber, which forces fuel out through the outlet check valve. When the priming pump is not in use, the hand knob must be screwed closed. This stops fuel leaking out past the plunger and also stops air leaking into the priming plunger barrel. This section examines the inline injection pump. Some diesel engines use inline injection pumps to meter and raise the pressure of the fuel. The basic principle is for a plunger to act on a column of fuel to lift an injector needle off its seat. Inside the pump is a pumping element and a delivery valve for each cylinder of the engine. The element has a barrel and a plunger that fits inside it. Their accurate fit and highly polished finish ensures only minimal fuel leakage past them without needing positive seals. The barrel usually has two holes or ports, called the inlet port and the spill port. They connect the inside of the barrel with the gallery. The gallery contains filtered fuel from the low pressure system. At the top of the barrel is a delivery valve holder, and the pipe to carry fuel to each cylinder. The upper end of the plunger has a vertical groove extending from its top to an annular groove. The top edge of this annular groove is cut in a helix, also called the control edge. Some pumps have a helix cut on top of the plunger. A camshaft, cam follower and spring move the plunger in a reciprocating motion. When the plunger is below the ports, fuel from the gallery enters the barrel above the plunger. This ensures the barrel is full of fuel. As the camshaft rotates, the plunger is pushed past the ports. The highly polished surfaces cause a sealing effect, trapping the fuel above the plunger. Moving the plunger further raises the pressure of the fuel. This forces the fuel out past the delivery valve along the fuel line to the injector. Fuel flows to the injector until the control edge uncovers the spill port. The pressurized fuel above the plunger then moves down the vertical groove to the annular groove and into the spill port. The delivery valve stops fuel leaking from the pipe back into the element. It reduces pressure in the fuel line to ensure there is no dribbling by the injector. The delivery valve has a relief plunger and a conical face which is held against its matching seat by the delivery valve spring. The relief plunger on the valve is a close fit inside the bore of the delivery valve seat. When the fuel pressure rises, the delivery valve is lifted off its seat. When the plunger is clear of its bore, fuel flows to the injector. When injection ceases, the pressure below the delivery valve drops to gallery pressure. Fuel pressure above the delivery valve forces the valve towards its seat. The relief valve enters the seat bore, sealing the volumes above and below the delivery valve. Further movement of the delivery valve towards its seat increases the volume in the injector pipe and reduces the pressure in there. This drop in pressure causes the injector needle to snap shut, helping to prevent fuel dribble from the injector. The conical face of the delivery valve then contacts the seat, further sealing the plunger from the injector pipe. Rotating the plunger controls the length of the stroke for which the spill port is covered. This is called the effective stroke. It influences how much fuel is delivered to the injector. A short effective stroke means a small amount of fuel is injected. A longer effective stroke lets more fuel be delivered. To stop the engine, the vertical groove on the plunger is aligned with the spill port, which stops pressure in the barrel rising. The plunger is rotated by a control sleeve, a rack and a pinion. Moving the rack rotates the pinion, the control sleeve and then the plunger. The rack's movement is controlled by the governor. This section examines the distributor type injection pump. The distributor type pump uses a vane type transfer pump to fill the single pumping element. This then raises fuel pressure to injection pressure. A distribution system then distributes fuel to each cylinder in the firing order of the engine. The most common type in light automotive use is the Bosch VE pump. A drive shaft driven from the engine rotates a plunger and a cam disc. Cams on the face of the disc have as many lobes as cylinders in the engine. A plunger spring holds the cam disc against rollers that rotate on their shafts. The lobes move the plunger to and fro in its barrel, making it rotate and reciprocate at the same time. Its rotation operates the fuel inlet port to the pumping chamber, and at the same time distributes pressurized fuel to the correct injector. The reciprocating motion pressurizes the fuel in the pumping chamber. The plunger's pumping action forces fuel through a delivery valve to the injector. This pump is for a 3-cylinder engine, so it has 3 delivery valves. The barrel has 1 intake port and 3 distribution ports. The plunger has a central passage, a connecting passage to the distributing slit, and a cross drilling to a control sleeve. As the plunger rotates, each intake slit aligns with the intake port, and the distributing slit with the distributing port. As the plunger rotates, the intake slit moves away from the intake port. At the same time, the plunger is acted on by the cams, causing it to move axially along the barrel, pressurizing the fuel in the pumping chamber. The distributing slit now uncovers the distribution port, and the pressurized fuel passes through the delivery valve to the injector. Further rotation of the plunger closes off the distribution port and opens the intake port. At the same time, the plunger spring moves the plunger back along the barrel for the next pumping stroke. For intake, fuel from the feed pump reaches the open intake port in the barrel. The intake slit aligns with the intake port, and fuel fills the pumping chamber and passages in the plunger. For injection, the plunger rotates to close off the intake port and moves along the barrel to pressurize fuel in the pumping chamber. The distributing slit aligns with the distribution port, and the pressurized fuel forces the delivery valve off its seat and reaches the injector. In this phase, a cut-off port in the plunger is covered by the control sleeve. To end fuel delivery, the plunger's cut-off port moves out of the control sleeve and lets pressurized fuel spill back into the pump housing. This relieves pressure in the pumping chamber, the delivery valve closes, and injection ceases. Metering the fuel is controlled by effective stroke of the control sleeve, and that's determined by the action of the governor sliding the control sleeve along the plunger. Sliding it one way opens the cut-off port earlier and reduces effective stroke. Sliding it this way delays its opening and increases effective stroke. The governor changes the position of the control sleeve to vary the quantity of fuel delivered according to throttle position and load. When the ignition is switched off, an electrical solenoid closes off the intake port and stops fuel delivery. This section examines diesel fuel injectors. Most diesel fuel injectors use the same basic design made from heat-treated alloy steel. The actual shape will vary according to the application. The injector assembly has several main parts. The nozzle assembly is made up of a needle and body. A pressure spring and spindle hold the needle on the seat in the nozzle body. A nozzle holder, sometimes called the injector body, may allow for mounting the injector on the engine and some method of adjusting the spring force applied to the needle valve. A cover keeps out dirt and water. The injection pump delivers fuel to the injector. The fuel passes through a drilling in the nozzle body to a chamber above where the needle valve seats in the nozzle assembly. As fuel pressure in the injector gallery rises, it acts on the tapered shoulder of the needle valve, increasing the pressure until it overcomes the force from the spring and lifts the needle valve from its seat. The highly pressurized fuel enters the engine at a high velocity in an atomized spray. As soon as delivery from the pump stops, pressure under the needle tapered shoulder drops, and the spring force pushes the needle down on the seat, cutting off the fuel supply to the engine. Some of the fuel is allowed to leak between the nozzle needle and the body to cool and lubricate the injector. This fuel is collected by the leak-off line and returned to the fuel tank for later use. There are two main types of injector nozzle, hole and pintle. Hole-type nozzles are commonly used in direct injection engines. They can be single-hole or multi-hole, and they operate at very high pressures, up to 200 atmospheres. They give a hard spray which is necessary to penetrate the highly compressed air. The fuel has a high velocity and good atomization, which is desirable in open combustion chamber engines. In pintle-type nozzles, a pin or pintle protrudes through a spray hole. The shape of the pintle determines the shape of the spray and the atomization of the spray pattern. Pintle nozzles open at lower pressures than hole-type nozzles. They are used in indirect injection engines, where the fuel has a comparatively short distance to travel and the air is not as compressed as in the main chamber.